Okay. Thank you very much all for joining us today for this beautiful 11th quantum webinar on the quantum internet and networks that we organized in Quantix, an association of École Polytechnique alumni, and together in collaboration with the Aristotle Association and also Pole Systematic Association. We are very happy to welcome you today. We have prepared to you a beautiful program with extraordinary speakers, and we could share with you their experience, and you also will be able to ask them the questions. So please, all the questions that you have, don't hesitate to post them directly onto the comment band on the right side of the YouTube screen. We will receive them immediately, and so that we will be able to post them to our speakers. And without giving a long introduction, I just want to present you representatives of our co-organizing association is Christophe Calvin from Aristotle, Jean-Luc Bellat from Pole Systematique, and Alexander Krasenbrick from Quantix. Guys, please give a couple welcoming words to our speakers and also introduce your associations before we start. Let's start with you, Jean-Luc.
Okay,
Please,
thanks a lot. Thanks a lot, Alvia. Do you hear me? Yes? Okay.
Yeah, sure.
Okay. We are very proud to co-organize with you today this webinar on quantum internet with Aristotle, Quantum X, and the Région Île-de-France. So quantum communication, quantum devices, quantum processing, and node transportation are key topics for the systematic cluster. As you know, or you don't know, but we are a cluster focused on deep tech, and we have several hubs. One focused on optics and photonics, where we are looking for quantum devices and quantum processing. We have also a hub for cyber security, where we are looking for post-quantum cryptography. And we have a hub dedicated to digital infrastructure, which is addressing all the transformation of the digital infrastructure. And today, one hot topic is about internet quanting. And there is a project under organization this year called QCI, led by Orange and funded by the Région Île-de-France, where we plan and we have the objective really to do a first in the world in terms of transportation of quantum information. So quantum computing is already a hot topic in research and entrepreneurship since years. It's really a new way of processing are expected, and this will have a significant impact on the way we will implement artificial intelligence application in different parts. So the new step is really about the transportation of entangled photon with a huge technical challenge behind this. And if we are able, and probably it's a program for a decade, but if we are really able to transport quantum information, we will create really a new architecture for the quantum internet. So it's a very hot topic for the future. It's a hot topic everywhere in the world, but Europe is very active, and it's very nice to see in the webinar organized today all the different people in Europe active in this segment, and it's very important to connect the best in class in this segment. So I'm really happy to listen and to hear all the information. So it's what
Thank you very much.
Systematic.
Thank you very much, Jean-Luc. So now we have already 68 person who is watching us directly in the stream. So Christophe, the floor is yours. Please give us an introduction from the Aristotle Association and welcome our speakers as well as on your side.
Okay, thank you, Elvira. So thank you to everybody who assists to this webinar. I'm very happy to see how many people are already joined this webinar, and I hope you will be interested in. So just 2 words about Aristotle Association. Aristotle Association gathers different organisms, institutions, industries, and so on, who are interested in digital technologies, since we are much more focuses on digital technologies and how digital technologies are make some transformation and big transformation in our society. So of course, quantum technologies are at this time, let's say, a big revolution to all this digital technology. So we had already one seminar on our webinar about much more quantum computing. So I think with the co-organizer, we thought that it was very interesting and very important also to focus on other quantum technologies than only quantum computing, since quantum internet, but also quantum sensors are very, very important in this digital transformation coming. So once again, thank you to the organizer for this webinar, because I think it will be a very interesting one. And I'm sure that you will be very interested in all this topic and beautiful speakers. So thank you very much, and have a nice webinar.
Thank you, Christophe. And now the tour of Quantix. I have a double pleasure to present you my comrade, schoolmate, Alex, who is also a Cambridge Quantum Computing Fellow and co-founder of the Quantix Association, and also a General Secretary. So Alex, please, the floor is yours. Present to us the Quantix.
Thanks, Elvira. So as Elvira said, I'm the Secretary General of Quantix. This is an alumni association from the École Polytechnique in France that we started a bit more than a year ago with Elvira and Christophe Jurzac, who will be a speaker at the end of this webinar. And the idea when we started this association was to foster the quantum ecosystem in France, the ecosystem for quantum technologies and quantum communication, everything that is around quantum. And I think we're at the right period now to see the evolution of the quantum technologies in many industries, not only in particular niche industries, but this develops in many other industries like the oil and gas industry, energy industry, finance industry. For the last year, we have organized mostly webinars, and more recently we focused towards students. And that's why the last weekend we organized the first Quantum Hackathon of 2021, where we gathered a bit more than 40 students to actually work on real quantum computing problems that were proposed by IBM, Pascal, Atos, Microsoft, and Cambridge Quantum Computing. And our plan for the next year, and even more after this, is to organize more and more activities to gather all the job offers for the students to really create an ecosystem that will thrive in France. Thank you, Elvira.
Okay, thank you very much, Alex. So once again, as I said, with Alex, we will co-animate this webinar today. And myself, I'm Elvira Shishenina, president of Quantix. And once again, I'm very happy to welcome you today as well, together with all our speakers on this webinar. Just quick remind you once again, don't hesitate to post all your comments and questions onto the comment bar here in YouTube. We will receive them immediately, and so that the speakers will be able to ask them. So this YouTube link, you can save it because the stream will be saved on this Quantix channel, and you could go back to it if you forgot something or you really loved the webinar, so you want to rewatch it once again. Okay, no more words, no more big introductions. Alex, I let you to introduce the first panel of speakers to us.
Thanks, Elvira. So today is about the quantum internet. So when one talks about quantum internet, one needs also a network around this. And if we want a network, we have to build them. So the first speakers of today will be about how can one build a quantum network. So we'll have speakers spread over different continents and different time zones, from Singapore, Germany, and France, for instance. So we'll have Frank Depper, we'll have Chunyang Loom, and Virginia Aria. So Frank will start its first presentation, and don't hesitate to post any question on the YouTube channel, and we'll ask them to the panelists. So Frank Depper is a group leader at the Walter Meissner Institute in Germany. He has worked in various parts of quantum technologies, mostly on the experiments side. He has worked on film deposition, structuring, material science, cryotechnology, microwave technology, and quantum science and technology for superconducting circuits. And in particular, he has implemented secure quantum communication in the microwave band. So please, Frank, tell us a bit more about this, and tell us, for you, what is the definition of a quantum internet and how do you want to achieve this?
Okay, thank you very much for the nice introduction. I'm very happy that I can present my and my group's perspective on a very particular and novel part of the quantum internet ideas, which is our work towards quantum local area networks, which naturally work with microwaves. So propagating microwaves are actually omnipresent in our classical life. So for example, in cell phone, in mobile communication, we can imagine them as such sinusoidal waves, right? In sensing, like radar or science, but also in things we don't really see in everyday life, such as supercomputers for distributed computers, but also in our local area networks at home. And our idea is now to apply propagating quantum microwaves for enhanced performance. The frequency is roughly 6 gigahertz, and to give you a picture, this is 5 orders of magnitude smaller than the telecom signals, which are at roughly 200 terahertz. So this comes with a big challenge, and this is the low photon energy. So we require cooling to 50 millikelvin to avoid thermal noise. However, this is a bit more expensive, of course, than room temperature experiments, but it's commercially available technology. And now we can come to the benefits. This means that because we're based on superconducting circuits, we can make deterministic protocols. We do have low-loss transmission channels, so superconducting cables are comparable to, say, I would say, standard optical fibers with less than 2 dB of loss per kilometer, and our free space range is roughly 500 meters. We are in the natural frequency range for quantum radar, but this is not today's topic. And we are, very importantly, in the natural frequency scale of the currently most advanced quantum computing technology, which are the superconducting circuits, where I show you here some pictures you may have seen in the news on the right side from big companies. And the state of the art here are processors with at least or with roughly 50 qubits, and one can do 10 to the 4 quantum gates in a coherence time, and quantum supremacy has actually been shown there. So here the 50 millikelvin cryostats are required anyways. They don't come on top. We have no frequency conversion losses. This is very important because this is a very big bottleneck to optics, where the microwave to optics transduction is has an efficiency currently of 10 to the minus 5 or worse. So this is the only option to reach 99% or very high remote gate fidelity within a few years, in my opinion. So the first step towards a quantum internet, in my opinion, is a quantum local area network. We have a Gaussian entanglement source, and the list is only to show you that we are pioneers and experts. Of course, we can do with that, we can use this as a resource, entanglement, to connect quantum computers for a quantum local area network or quantum supercomputer, even in a distant future. We can do quantum radar type sensing, but we can also, once we are at it, do quantum communication as you used to, so free space microwaves or microwave QKD or QKD via our superconducting cables. The state of the art is that we can do some very fundamental protocols. We have done secure remote state preparation over 36 centimeters in a fridge a couple of years ago, so 1.5 years ago. And very recently, we have managed to do quantum microwave teleportation over a very similar distance. The hardware we are also developing very actively. So we are currently setting up a 6.6 meter millikelvin cryogenic link between 2 such millikelvin cryostats, which could in future host superconducting quantum chips. This is in the framework of our quantum flagship project QMIX. This brings me to the end of my small overview. In a summary, I hope I could somehow show you that microwaves are very important in classical communication and sensing and computing. Quantum microwaves can enhance these applications via entanglement, and we have demonstrated this possibility already in the lab. And quantum local area networks are technically very well conceivable and are a very important first step towards a full-fledged quantum internet, because the key in a quantum internet architecture, in my opinion, is not the distance as a first step, but it is to connect actually superconducting quantum computers via remote gates with sufficient fidelity. A more distant application could be superconducting quantum supercomputers, and similar to classical supercomputers. And these networking tasks, of course, are difficult at optical frequencies in near future, because the optics to microwave conversion is very inefficient to date. Thank you very much, and I'm happy to take your questions and answer to them.
Thanks a lot, Frank. I actually have a question for you. So you say you're working on local quantum networks, and you have implemented this secure quantum communication in microwave bands. So this is some kind of a new architecture. Why is it a crucial step to build a distributed quantum computing network? And could we possibly in the future try to match superconducting devices with cold atoms, for instance?
Okay, these are two very different questions. The first thing, yes, the microwaves are a rather new frequency range in the business of quantum communication and quantum internet, and therefore demonstrating a fundamental protocol such as remote state preparation over some macroscopic distance, even inside a single fridge, was a very, very important first step 2 years ago. So this was the basis to move on with these activities. And matching this with other platforms, this is of course very interesting. The most natural match will be when another platform has direct access to microwave. So like NV centers, for example, or maybe this could even be possible with cold atoms. But converting to optics, in my experience and what I've seen in the last years, is still a difficult step. For this reason, for now, I'm advocating the quantum local area networks as sort of a third leg in addition to QKD and long-distance quantum internets.
Thanks a lot. Is there any question on the YouTube side? You can post any question you'd like.
Thank you very much, Frank. For instance, we don't have questions from the audience. Please don't be shy. Our speakers are very open and excited to share with you their expertise. And we will be back to you, Frank. But for instance, I think we can give a word to Chunyan to introduce himself as well and to introduce the spectral. Hello, Chunyan.
Yes. Right. Can you hear me?
Yes, we can hear you perfectly.
All right, great. Thanks a lot for the invitation. Very happy to be here to share a little bit about myself, the company, and what we're trying to achieve at Spectral. So Spectral is essentially a spin-off company from the Center for Quantum Technologies. And we're focusing on building space-qualified quantum entanglement sources, that can fly in a space environment, right? And here, I'll show you, kind of bring you through a little bit of what we've been doing over the past years. So as a spin-out company from the Center for Quantum Technologies, we are leveraging a lot of the heritage and the research and development already being done at CQT. And really benefited from the years of hours and years spent in the lab developing these enabling technology. So in this slide, there's two important things to highlight here. On the bottom panel, you can see bottom left. This is a classical kind of lab-based quantum entanglement experiment using spontaneous parametric down conversion SPDC sources. A blue photon getting split into 2 red photons. The team has essentially done a key thing in miniaturizing the desktop size experiment into a device that's around 20 centimeter by 10 centimeter. That's the first step, being able to kind of string the component into a tight space. And the second step is to make it really, really rugged in terms of designing the layout. and the use of the components to make it really rugged, testing it on the ground for vibration and for kind of the space environment testing. And then with the aim of launching it to space to show that quantum entanglement can be done in space. So you see here on the top panel, through the last 8-10 years, several experiments being done in sequence to really bring up the level of the technology in terms of ruggedness and miniaturization. The last result, the last satellite we launched was the Spooky 1 satellite in 2019. And that was successful. A little bit more about that in the next slide. And right now we're planning 2 missions that will go up in around 2023 timeframe. There's 2 missions here. One is called the Singapore UK QKD CubeSat mission. So this is a collaboration between CQT, the Center for Quantum Technologies, and its counterpart in the UK. More on the academic side to showcase QKD over long distances. And us as a company, we are planning a spectral one with a more industry and use case focus objective. Okay, here, just to rewind a little bit. So Spooky 1, you can see here the picture. So this is the picture here you see is Rob Bennington, our CTO. He was the one kind of leading the satellite mission back at CQT. Now, obviously, he's joined Spectra as a co-founder and CTO, holding that small, we call it a 3U size CubeSat. The satellite itself is literally 30 centimeter by 10 centimeter, so very small, very compact. And then the other picture shows that the satellite being launched from the International Space Station. So as of now, I think we have successfully completed a demonstration of the entangled photon source in space, violating Bell's inequality and so on. And right now, I think it's been more than 18 months in operation. So we're studying kind of the degradation effect on the quantum device, how it performs, alignment, entanglement, the fidelity, how that changes over time whether it's affected by in the space environment. And I guess to fit into the broader framework of the previous talk and what we're talking about today, quantum internet is a very big theme, right? Building quantum networks. There's a lot of very interesting things that is currently being researched, being pursued right now, all over the world. We hope we'll be contributing to a small part of that whole ecosystem. And the immediate kind of, as a company, we're also looking at kind of the short-term applications from the industry side, from the business side and use case. And we chose to focus on QKD, which is the nearer term market. But we also do have sights on, trying to contribute to the global quantum internet using our entanglement source and having, being able to distribute entanglement as a resource. But, this schematic shows kind of the immediate focus, which is essentially to try to link up to showcase satellite-based quantum key distribution across long distances. So this example here is between Singapore and Europe. We know that a lot of local kind of QKD networks are being formed. Here in Singapore, we have the National Quantum Safe Network. In Europe, you have Euro QCI and so on and so forth. So ideally, the satellite, the quantum optical receiver would be one of the nodes in the local network, and they'll be able to kind of enable QKD to be transmitted from Singapore to Europe and being integrated in the network. So in a nutshell, that's where we are, aiming to demonstrate this and showcase this particular technology to bridge long distances. And over the long term, hopefully working with partners and colleagues all over the world to really bring more applications or more ideas on the quantum internet to the community. And with this, I stop for a while for questions or for discussions.
Thanks a lot, Chun Young. I actually have a question for you. So the next major project for your company is the launch in 2022 of an entanglement-based encryption in a small satellite, a CubeSat. Could you tell us why this is a milestone for quantum communication and for the networks people want to build?
Yes, definitely. I think our key thing, so satellite-based QKD has been demonstrated by our colleagues from China. Very, very impressive work that they've done. Really kind of world-leading demonstrations. What we are trying to create or aim to kind of achieve here is having that perspective on potential commercial deployment and integration in networks. And also, part of this program is also to focus on, from the business side, the cost perspective, right? So we are trying to do it on a CubeSat, a small satellite. So, in parallel to this quantum development on the space side, there's this new space revolution as well. Really leveraging the CubeSat format, which is standardized, lower cost, quicker to deploy, and so on. So really adopting that mentality, launch and test and try. And if you fail, then launch again. So with the technology that we've developed, miniaturizing that quantum payload, we are able to fit on a small satellite. So overall, from commercial business perspective, trying to aim for a cost-effective solution for this long-distance QKD. And I think that's the next major milestone for us, is to bring kind of use cases with potential users to showcase how it can be used, how it can be integrated into the local networks, and so on. Yeah.
Thanks a lot. Once again, if anyone in the audience has a question, don't hesitate to ask them on the YouTube channel. We saw that there is a question from Deppe, and we'll take this at the end of this panel, if it's fine. So if at this stage there's no question, we can thank Chung Yang and ask our third speaker to step up. So the third speaker of this panel is there's actually a question. Sorry for Chung Yang. So the question is the following, please. Have you ever tried the OTP in QKD via satellite?
So for one-time pad, right? Yeah. So I think the most basic form is to distribute the keys to the end parties. In what mode or how they want to use the raw bits, right, as their key is really up to them. For OTP, yes, potentially, the keys delivered can be used as OTP. Again, I think it really depends on the size of the messages or the size of the data that you want to encrypt. OTP may not be viable or kind of cost effective in terms of encrypting large volumes of data.
Okay, great. Thanks a lot for this answer. Very clear. So on this, I think we can go to the third speaker, Virginia. So Virginia, she's an associate professor at the Institut de Physique de Nice, and she has worked extensively on what is called now the Nice experiment. So her work is quite complete. She has worked both on theoretical and experimental quantum optics. Since 2010, she has developed a project on quantum communication synchronization. And since 2015, she has driven a new research program on continuous variable quantum optics, exploiting guided wave optics as well as quantum photonics on different integration platforms. So we're really happy to welcome you today, Virginia. So please tell us about your work and about your view on the quantum internet.
Okay. So I'm talking you today about our project, which is developing Nice, and it's a team project. So it's led by our team leader Sébastien Tanzili, but it has the support of all of the university, and we are all involved in different level in this project inside the group. So the basic idea is to develop in France and working QKD link, exploiting entangled photons. And main objective is to have a test bench for a different configuration and systems we are developing in the local area. So I just briefly introduced the basic ideas. The link will be based on entangled photons. We generate entanglement following a very well-assessed strategy that it's kind of our specialty in NIS. And it's entanglement generated by simply pumping nonlinear components, and under appropriate condition, this can generate paired photons. So once you have the paired photons, what you do is that you split them. You separate them because of their different colors, and then you send them one to a partner of the communication and the other one to the other one. So the idea is doing this on a 3 nodes networks. We will have a node that will be the one of the source, and the other one that will be the nodes of the two communication partners that we will call Alice and Bob. This will be developed in the Nice metropolitan area under 30 kilometers. Of course, it will be on, of course not, it will be on optical fibers. So we generate the photons at a wavelength which are compatible with low losses in the optical fibers. And for this, we have a collaboration with the group Orange, which is giving us access to a deployed network of fibers which are already installed among the 3 sites. Once the photons are distributed on this connection, what we do is that we detect them. So we exploit a correlation which is called energy time correlation. So what we are interested in is in exploiting. Essentially, we have measures which are based on the detection of different. On the correlation among different detection times and photons of different sites. And so this is a quite well-assessed strategy, so we can exploit this. And for detecting this photon, we need a very high-quality detector because, of course, if you have a detector which we are not efficient, you lose a part of the information. If you have, and then you leakage you can virtually leakage some information toward some spies. And if you have a detector which has dark count, you increase the rate of error on the whole communication. So we have a collaboration with this for the group IDEC Antique, which is based in Geneva, and that are providing us, with whom we are developing they are giving us the detector for the single photon detection. And then, so we are developing the entire chain of communication. This will be, we are developing all the electronics, all the communication channel, classical communication channel that are needed to share the information, the relevant information between Alice and Bob. As I told you, this is a project that is a very, it's a project of the Nice area, and we are many persons in the group. There is a PI, of course, but many in the group. We are all doing some different parts. The longer term idea is that we have in this way an on-field deployed test bench, and then we can use it to, of course, it's interesting itself to develop this kind of network in France and in Europe. But we have, in this way, the possibility of testing on this functionally network components and systems that we are studying right now in the lab. For instance, a perspective could be to employ, since it's a network which is based on entanglement, we are thinking about improving the performances of the network by making an entanglement swapping configuration. And in this case, it can be shown that this is very well adapted to long distance communication, as it reduces the rate of dark count on the link. So as a matter of fact, it improves the signal to noise ratio of the communication. Another plan that we have is that we can test the components which are developed in Nice. Up to now, all the network is based on off-the-shelf components, which of course we selected and tested and we validated in the lab. But a perspective could be to introduce inside the network components that are homemade in France and in Nice. For instance, like photonic circuits that can implement some special function at the different nodes of the the connection. And on a longer term, we have the project to realize, let's say, hybrid systems in which we have a connection among the local area network in Nice and the local area network in Paris, similarly based on fiber systems via satellite. And for this, we have a collaboration with Thales Alenia Space, which is now just starting. So we hope we can also do like this kind of hybrid systems. So I don't know if you have any question. It's a bit shorter than the other.
Thank you very much, Virginia. And I guess we have one question from the audience, and then I also have a couple questions, but to all the speakers. So I displayed it right here as a question from Michel Courec in France. ANSSI is cautious on the QKD, same as in the UK, especially regarding the associated cost when it will be potentially commercialized. Is the cost criteria is taken into account in the research or not? Could you please comment on that?
Okay, of course, this is kind of an ambitious problem as a project, so it demands some fundings. What we took care of doing is to implement all the network with the commercial systems. So a lot of systems are already, it's not research grade, it's really off-the-shelf systems, and so that can be kind of inexpensive of the basic. Everything is based on optical fiber. So we have fiber components which are not really expensive. What can be, of course, more expensive is the detectors. That's why it's important because it's important to have a high efficiency and low noise detectors. So this can be a bit more expensive. And of course, it's important to have access to the fiber which is already installed. Otherwise, the infrastructure is not something that you can just put in the middle of the street in Nice, as you can imagine. So this is in this sense, it's a cost. But as I told, everything is based on solutions which are, let's say, already existing in some form in industry, and that we are employing for quantum scopes. So I don't know if I have a short reply for this. Of course, it's an ambitious problem. So in order to develop all this, you need to have some fundings as some starting funds, let's say. But then we took care really of using as much as possible solution that can be easy to implement in principle, even in different situations. And this is a bit the strategy of our group. We are always marrying quantum optics, and let's say fundamental research with components and systems which have already developed, but for something else. That's why we are working since a long time with telecom wavelengths and with the systems that are compatible with long distance fiber implementation. Okay.
Thank you very much. Oops, there is an echo. Okay. Yes, thank you very much, Virginia. And we have like a couple minutes for one more question. And since in the audience we don't have one, I was really wondering, so I'm trying to bring up all the speakers to the studio now. When it comes to the like security, defense, etc., so quite important topics. I was just wondering how this is affect, let's say, the scientific liberty, because it goes alongside with the questions of the sovereignty, etc. So how it goes with your scientific liberty or the academical research where you do sometimes. Are you restricted? Is the, let's say, the speed of research or the processes or decision making is much slower because of that? So could you please give a couple comments on that on your side? Let's start with Frank.
Okay. Yeah, so in my research and in my work, this issue has so far only popped up on the side because the TRL is not high enough. And we have plenty of civil potential applications. So in this sense, at this moment, I do not feel any restrictions. It may pop up in the future.
Okay. Chunyang?
Yeah, so obviously, I think there's this I want to say, this overhang of whether such technology could be sensitive or not. As a business, we are focused on being super neutral, right? We are a technology provider, a solutions provider. In the civil case, kind of just the commercial use cases. There are a lot of potential use case there, and I think as a company, we are primarily focused on that front. With some of the more sensitive requirements, obviously, I think we'll have to depend on individual kind of requirements and circumstances to navigate the environment. But I think it's a little bit, again, quantum technologies in general it's nascent. I think in general we should just have more collaboration now. And worry about things later on.
Okay, and now Virginia, your turn.
Support from our university, from public research, but it's true that it's a sensitive topic, and so there is a general interest in France also on these strategic topics, because it can turn out to be a topic that possibly, as you say, can have some hot point, let's say, from the point of security of information. We didn't have this kind of problem, but we are aware of the fact that it's potentially developing this. It's also a way to put France and Europe in the forefront of the research in this topic, so to gain, let's say, independence and to gain more and more strength with respect to possible attacks, to possible, issue that can come. But right now we didn't have any problem. On the contrary, we had the full support of our organization, and that's very cool because it helped us to develop our project
Activities. Yeah.
Yes.
Well, I think we are at the end of this first panel session. It was quick and very much interesting. So thank you very much to our awesome speakers for finding the time, because you are, as Alex said, all in a different time zone. So Chunyang, you are in Singapore currently, Frank in Germany, Virginia is in France. So thank you very much for your time, for your willingness to share with us your experience and your results as well. And hopefully we could see you soon for the next versions of these webinars, and maybe to have more longer sessions dedicated to your specific projects. Thank you very much. And now, Alex, please, the floor is yours to introduce the next panel session.
Just before going to the next panel, we have two questions from the audience, actually. So the first one is for Frank Deppe. So I'll just show it on the screen. It's a question about the conversion from microwave to optics. So the question is, converting to optics means converting from microwave to frequencies used in optics fibers?
Yes, actually, it means even more. Specifically, it means converting from microwave to optics and back without losing quantum coherence. And that's a very difficult part. And quite surprisingly, such frequency conversion over 5 orders of magnitude is the mainstream approach to networking, even superconducting quantum processors since years. However, we have to acknowledge that progress is quite limited, and for this reason, we are advocating alternative solutions.
Thanks a lot. And a really short question from Jonathan, and then we'll really have to jump to the second panel. So the question from Jonathan is, again, about QKD. So currently QKD is point-to-point. How to generalize QKD to different network topologies? I think the question is for...
This question is not for me.
Yeah. This question is for Chunyang.
Yeah. So you're right. Kind of QKD for now is point-to-point. Point-to-multipoint or kind of mesh network QKD, it still relies on single point-to-point link. Obviously, if you go for mesh network, the cost goes up because pairwise links are the devices required will kind of scale up. There's a lot of trials being done now on kind of let's say star topology, and then linking the backbone together. Having a central node and linking the central nodes together so that any points within the local star topology can reach the other topology, and then using kind of key management layer on top of it to kind of manage the keys. I think again, I think this may be related a little bit to the cost question somewhere earlier. With kind of scale with mass production, the cost can come down. I think for the other types of topology could be possible, but I think for now, I think we're still limited by a few constraints.
Thanks a lot, Chungyang. So on this question, we'll jump to the second panel, which is about the quantum security for networks. So we try to discuss how we can build a quantum network. So now let's discuss how we can make it secure. And for this panel, we have three speakers. We'll have Chris Irvin, who is the CEO of CET's Quantum Security, Mark Kaplan, who's the president of VeriCloud, and Lucian Commander, who previously had a technological background and is now a consultant at the BCG. So please, Chris, you can start. Give us a few minutes to introduce yourself, to know more about your background and your activity.
And I do the usual thing to make sure that you can hear me all right in these days of video messaging, yeah?
Yeah, it's going perfect.
All right, a couple slides. I'll try and be as brief as possible so that people can ask questions. Again, I'll just double check. Is that coming up? I got some slides. Yeah, there we go. Just a handful of slides on who CET is, really. We are, like many others in the panel, trying to combine the power of quantum technologies to solve some key problems. So the one we're tackling is how do we secure this beautiful 5G world that we're being promised with connected healthcare, connected transport, automated transport, and all the like, because our current techniques are rapidly sort of approaching an expiration date. So we've taken it as our mission at CET to protect what really is the world's most valuable resource now. It's no longer oil or gold, it's information from the threat of quantum computing. And it's not just quantum computing, AI, machine learning. There's a number of different threats that are starting to break our systems, really. Oops. A bit about who we are. I mean, we're a team of 12 at the moment and growing. So if you're interested in the area, we'd love to hear from you. Growing both on the commercial and the technology side. Some of our founders did the world's first chip-to-chip demonstration. So you're going to see a picture on the next slide, but doing quantum encryption, sort of quantum key distribution, quantum random number generation. But rather than some of the fiber systems, the bulk optic systems we've used in the past, I built some of these for my PhD as well, taking a chip-based approach that opens up a host of advantages. And this is really what we have to offer. We figured out how to miniaturize quantum safe hardware into a size, a form factor, and we have a crucial roadmap to a price point that makes it interesting to customers. Because right now these things cost, I don't know, 150, 200,000 US to buy a system. And clearly, if you're thinking about a telecoms network with hundreds of nodes, this is not a calculation that a telecoms executive really wants to do. They've got to come down by about an order of magnitude. And we think chips will help us with that. So we have two products that we're evolving into dev kits. We can do quantum random number generation, gigabits per second speeds, and our first device is picture like a graphics card, a PCIe card, because early customers want to buy development kits, trial them in their lab in a variety of use cases. And similarly for quantum key distribution, we've already heard some very nice talks that have introduced us to these concepts. We again have a chip-based approach where you have the laser on board. I think if you can see the resolution, those three prongs are an onboard laser that we can attenuate to the single photon level, imprint qubits on, and then distribute between two users secure keys. We're actually going to release earlier than a graphics card because we just want to get it out there into the wild. We're going to have like a 1U rack that'll be one of our first things, and then moving on to the graphics card. We have a nice roadmap for all this. And there was a pressing question there. I think it was maybe Jonathan asking about how do you extend beyond point to point, which is sort of If you take the classical analogy, that's like the bulletin board systems that I was connecting into in sort of 1991 and 2, the early 90s, to what we know today is this rich tapestry of connections in the internet. And part of that, we think, at CET is this chip-based approach, because it's really not so far off Control-C, Control-V to start sort of cutting and pasting and tiling these devices such that inside a future PCIe card is not just one fiber coming out, but it's 4 fibers coming out. And then you can either route them different ways to protect against DDoS attacks, or maybe they really are like your network devices now, where it's multi-in, multi-out. And so that's what we're planning for. What have we done and what are we looking for maybe to finish on? We're already working with some nice big names demonstrating. We flew our transmitter with on an Airbus drone, working with 2 other universities in ID Quantique to exchange key with the ground. And that's a simple demonstrator, but it's on the way towards some of the satellite systems that you've already heard from Shun and others. We have been working with British Telecom, and there's about 16 other project partners to get these things embedded into citywide test beds, because things work differently compared to when you have a lab and a fiber spool and nice temperature controlled to distribute it over a city with trucks driving over your fibers and temperature variations and all that stuff. So getting it embedded into fiber test beds and doing some use cases on top. And one of those use cases we worked with, Thales has come up a couple of times today as well. We were on their Cybrid Station F program which is a sort of an innovation program of Thales, and we met CryptoNext, which is a post-quantum algorithms company. And sometimes we're their competition, but they can also be very complementary as well, because all the post-quantum algorithms still need to start from good randomness to sort of bootstrap themselves. So we did exactly that. We plugged a random number generator into their algorithm, which they plugged into a popular sort of open source library. And we're doing a quantum safe digital document signing demo. And then maybe just to finish on, this is one of a key one that's up next, where in the Paris QCI project, there's this larger Euro QCI project that looks to put a quantum safe network down across Europe. And some of these things are already getting started at that sort of national level. So Paris is doing a network, sort of four nodes to start with many of the people you've heard mentioned before, sort of Orange, Thales, CryptoNext. And so this is really to lay down a real network, a bedrock from which you can build sort of quantum safe applications on top of. We're definitely looking for more end users to test out some quantum safe applications, because you're the folks with the real commercial problems that need to be made secure. And in terms of benefits from you, I mean, you get to explore early how to make your company quantum safe, because you probably already required some of these algorithms, depending on how secure and how long you want your information to be stored from securely. So certainly a plug in the Paris region, and there's other things happening as well if you're interested in getting involved and trying to figure out how to make your company quantum safe and building your own roadmap, because these things don't happen overnight. Information security is, for anybody who works in it, an intricate involved discussion. It's not just a simple point-to-point. There is no blueprint for the internet that you can sort of hold in your head. It is such a complicated beast. So my only words of wisdom is get involved early. But I'll leave it there in case there's any questions, or moving on to the other speakers.
I actually have a question for you. So what was the main challenge you faced when you wanted to create this quantum startup?
Well, all the normal things with a startup: finding funding, finding team members, setting your goals. Especially for us, I've been part of something called QTech at Bristol that has now created about 20 quantum startups. Most of these have a very academic bent to their first employees, and it's a different story delivering to commercial timescales than it is to delivering to academic timescales. So it's all the usual stuff with doing a startup, and that's already challenging enough. And then it's the added bits of what the heck is this quantum stuff? You're trying to do a lot of education, but thankfully, I mean, it's now quite timely. You see a lot of people talking about quantum computers in the media, and both the pros, which is drug discovery and that kind of thing, but also the negatives that are going to come with it in terms of having to upgrade security. So some of that's being done for us, but there's certainly a huge piece of educating customers, and security is one of those things where it's a cost and people want to decrease their costs, but a bit of planning now. It's sort of that old old recommendations. A bit of planning now can save you a lot down the line. But us and others are having good experience with this now. Great question.
Thank you very much, Chris. I also have a question on my side, maybe quite tricky one. Your CET's portfolio includes like many contracts and partnerships with the companies, like on defense, like governmental organizations as well. So, well, we won't ask you maybe for some privacy reasons about the details of these partnerships, of course, but in very general way, what are the key ingredients to convince such organization to launch quantum, to go quantum, especially that now there are a lot of hype about the technology. No one knows when it will bring the advantage. So how do you convince them?
Part of it is this education piece. So one of the best conferences I know of for quantum security, quantum safety, is the ETSI IQC quantum safe workshops that are held yearly. When I presented about 2 years ago now, there's Bob Blakely from, I think, Citigroup at the time that walked through step by step. Here's a plan of how a company can start to take stock of the problem. What is all my equipment in the field? What is the problem? And as soon as you start to do that, any company, suddenly the eyes open up and you're like, oh, okay, this is going to take a couple of years. This is going to take some money. So that's sort of step one, is education. And that's a great example. And I think those slides are freely available for any companies that want to start bringing this up to sort of a boardroom level with a strategy. The second bit is getting across. Startups are like this key insulating layer. So in the UK, we've had these hubs that have gotten the technology to a certain TRL level, which has been great. And you've had the big businesses like Thales, like Airbus, that want to take them in. But there's still this divide because academics will produce something to the point of getting a paper, and then they sort of lose interest a little bit. But that's not yet ready for a big company. They need version things. They need, they're going to get this first one, probably break it and hand it back. And this is where startups can come to play. And I think big companies are getting that for a very modest sort of initial proof of concept. I mean, we're talking as little as sort of $5,000, $10,000 or something. They can start to play in an arena, very low investment, but that's music to a startup's ears to then go to an investor and say, we've got customers, we've got revenue, and suddenly the investors now are paying for the R&D that otherwise a big company or a small company would have to be paying for to develop these solutions in-house. So there's no one silver bullet. It's a lot of educating, a lot of getting that message across, because this also holds true. It brought up the ANSI, the NCSC white papers and QKD. They raise quite important challenges that quantum encryption hardware has, and sort of CETS has set itself up to address many of these challenges. And maybe the only piece that's missing is, it's like any new technologies, maybe it needs to do some steps to get ready for the prime time. But what is needed, this is what's missing from these statements, is innovation from early testing, not on mission critical information yet, but in test beds. And this is where companies can get involved. And that's my only complaint against those, is it doesn't push enough the need to consider all the opportunities that are out there, the ways of solving this problem, because it might not be exactly our devices that solve it, but maybe parts of them, and then you add something else, and then you add something else. And you only know that by end users, customers, manufacturers, all getting involved into this wonderful sort of innovation, self-fulfilling sort of loop. And that sometimes gets missed in some of these white papers and stuff.
Great answer. Thank you very much, Chris. And maybe we can answer the same question to our next speaker, right, Alex?
Yes. So the next speaker is actually Mark Kaplan, who's the president of VeriCloud. And we're super excited to hear about your story.
Let me share a few slides. Hi, everyone.
Thank you very much, Mark, for joining us.
Sorry, that's the one.
Once it's ready, we bring your slides to the screen.
Here.
Okay, I guess we see it.
Okay. So I'm Mark Kaplan. I'm the president of VeriCloud. We are a company working on quantum cybersecurity. Probably what distinguishes us from a company like CET or other companies in quantum communication is that we have this very strong focus on applications. So we're not producing new hardware for quantum communication, but really try to focus on what are the right use cases and how can we use existing technologies to address new use cases. So who we are, first, let me start by presenting my co-founders here, Elam Kashefi and Joshua Nunn. So with this respect, we're also very complementary with CET, because we are a French company with a foot in UK. Elam and Josh are both academics in France and UK, respectively. Since we created the company, we've been associated to actually most of the projects that are related to quantum internet type technologies. Probably the most relevant today are the Quantum Internet Alliance, which I will mention a bit later, but also the Paris Region QCI, which was mentioned in the previous talks. So within this project, what we try to develop is this view on applications that can be run on quantum networks. And we are developing this view at different terms. So we have this focus on application, and what we see as the relevant use cases, what we try to do is classify them, whether it's for the short term, the midterm, or the long term. So in the short term, these are the product that we are commercializing right now. What we are working on is a new quantum network architecture that we like to think about as the quantum Ethernet, with a very specific application, which is lifelong secure storage. So the application itself is not new. This is something that exists already. But what we do is really like a quantum network architecture that is better suited for such applications in some cases. In the midterm, we are doing a lot of work to classify and try to understand what would get us from the current situation, where what we can build our QKD networks basically to a quantum internet. And in the long term, one topic that is very interesting for us and kind of in our DNA is the topic of secure cloud computing. So let me just very briefly give you a hint of what these topics are, and then maybe I can come back to the slides later if people have questions. So the idea of a secure quantum cloud is very beautiful. It's a very beautiful mathematical idea, but it's also something very interesting to do in practice. What we know is that when we use quantum computers over the internet today, for example, the one by IBM, what we do is just sending the program on the clear. And secure cloud computing means what we want to do is to send an encrypted version of the program to the quantum computer. And it turns out that if you have a quantum connection between the client and the server, you can do these operations kind of in an easy way with a technology that is similar to QKD technology, meaning something that we can start investigating today. Regarding applications, what we are doing is trying to classify those first and try to understand, as soon as new pieces of hardware will become available, what are the corresponding applications. We have a very complete website on that. We're hosting this website, but it's developed in the context of this Quantum Internet Alliance that everybody can consult and check what are these protocols that you can run at various stages of the development of quantum networks. And in this context also, we wrote a report that should be published very soon, in which we identified some major challenges that we will be able to address with the technologies developed over quantum internet type networks. They don't all use the full-scale quantum internet, but some pieces of hardware that we might not necessarily have today. And these are pure research questions, but on the application side. And finally, the short term for us is really this notion of an Ethernet. It's quite different from what Frank Depé has showed earlier. Actually, it's more related to one of the questions that was asked in the chat. It's a new network topology. We use a line and we develop all the abstract layers of the network, meaning the architecture, the software, the protocol, and applications to be able to have a fully meshed network with a single line of fiber. So it's a new type of network architecture, and what we develop on top of that are applications related to key exchange, of course, but also to secure storage, with the idea that using quantum technologies, you can get lifelong data security, which is something that is very hard to achieve with classical technologies. Okay, let me stop the sharing, see if there are a few questions, and I'm happy to go back to the slides if I can use them later.
Thank you very much, Mark. Yeah, oh, sorry. So yeah, thank you very much,
thanks,
Mark.
Mark.
So, Alex?
Actually, I have a question for you. What is the milestone you dream to achieve, if you could, with your technology?
So you mean for our technology, or for the quantum internet in general?
With your technology.
Okay, so with our technology, what we are trying to achieve and demonstrate, so we have this idea of a local area quantum communication network, and what I think is important here is that we've heard of state programs and sending satellites to the space, but the message that we're trying to pass is that you can also start your own quantum network at a local scale. We make it affordable for these companies. We've optimized all the elements, and it's kind of a bottom-up approach toward this quantum internet, as opposed to a top-down where you have to send satellites and connect long-distance points. So the milestone that we want to reach is when these two will connect, right? Because this is when we get to a full-scale quantum internet, basically.
I have a question on my side as well, Mark. So usually new technology, we can often observe it in the industry. In order to be well integrated, it requires already prepared infrastructure, right? New protocols, new hardware, etc., etc. And sometimes it happens that we have a technology which is very well developed, but we just don't have a ready infrastructure. So it's like a chicken and egg problem. We don't have a demand because we don't have an infrastructure, and we won't build an infrastructure since we don't have a demand. So how it relates to actually quantum networks, Dom, and maybe you can connect on that, or how do you resist it? Or maybe you're waiting for like an quantum Elon Musk, who will come and who will build like charging stations in all the countries so that we can bring like cars. So.
Well, I think that regarding the quantum networks, what we saw already is that there have been progresses, right? We've heard already of many of them, the Paris region, the Nice region, the Singapore region. So there are lots of quantum networks where we can start plugging in the technology. And of course, the next step is to get users to connect to these networks. But I wouldn't say that it's not really a chicken and egg, in the sense that each of these small progresses matters in this with this respect. So no, I'm quite confident that these networks will grow and connect to each other. But the main issue not issue, but what we really think is the key point for us, right, is to also be able to identify exactly what are the gains for the users. So there's a lot of education to do, but also a lot of engineering for these solutions and research also for future challenges.
Okay, great. And I guess we have a question from the audience. In creating a new type of network, does your technology replace the traditional router or switch?
Actually, no, it's quite different. It really, so what was mentioned in the previous roundtable is that this kind of networking topology in standard QKD networks is achieved by delegating everything at the key management layer. What we do is pushing it down to physical layer, a bit like in a traditional router or switch, except it's a different type of technology. But we have an explanation on our website. I don't want to go into technical details.
Great, thank you so much. Thank you so much, Mark. We can switch to the next speaker. Great. The last one in this panel session.
Hi. So we have Lucien Commander, who's working at the BCG, and of course, when you're talking about quantum security for networks, as Chris said, at the end, everything boils down to the user, to the endpoint of the network. So Lucien will actually tell us about how this ecosystem can interact with the major player in the industry.
Super. Thank you very much, Alex. And I just want to be sure, can you hear me properly? Super. Then I'll start by thanking you for having me on the panel. And I wanted to make this as interactive as possible. So I've just prepared a small slide just to, let's say, better introduce myself. So I'm currently a consultant at the BCG, Boston Consulting Group, and this is a management consulting company. And I have another hat, which is deeply rooted in the QKD area. But at BCG, I was very lucky because I get to experience how actually the other side, and by the other side, I mean, let's say the commercial enterprises, how do they see this developing quantum technologies landscape, and how do they perceive it at a board level room, as opposed to how I looked at it and how I saw it when I was a scientist. Prior to my current life, I used to work at Huawei, where I developed a lab on quantum technologies, and there we looked at continuous variable QKD systems. So we developed telecom-focused, let's say, QKD systems, and then we had a successful field trial in Spain, where we've had an integration with the software-defined network. So that was a pretty high TRL, and that was more than 2 years ago. And prior to that, I used to work at Toshiba in Cambridge, where I developed advanced quantum communication systems, single photon detectors, and pretty much whatever was needed to develop the system. And I also have a PhD in quantum technologies and from Cambridge and MRS in photonic systems. I don't want to spend too much time on this, and I'm actually looking forward to receiving some more questions from the audience, just so I can gauge my time, as I know that we're actually running a bit behind schedule. So I'd actually like to open the floor for questions if there are any from the audience.
Actually, I have one for you, Lucien. So as you said previously, you were working as a scientist in quantum technology. So what did motivate you to actually transition from the science part to the business part?
Yeah, that's a good question. Somewhat the answer is very personal in many ways, as I'm sure life in academia for many people who are working in R&D is a different experience for everyone who's going through it. And when I decided to make this switches was for personal reasons. But what I can say particularly is that the two worlds are very different. So and I think Chris kind of alluded at it earlier. People in the R&D, so in industry or in academia, when they develop something, they look at it very different from how companies, or let's say end users, or the first end users will look at quantum technologies. And being able to see how people look at these things and to be able to learn these two different languages, because in the end there's kind of two different worlds that need to be bridged, that is something different and also something very interesting. And that was one of the personal reasons why I decided to do this.
And you're saying that, okay, these are two different worlds that communicate a bit differently somehow. But we're seeing nowadays more and more startup companies getting built out of academic research, right? So
yeah.
What do you think is like the learning process of these people to enter the business side of it?
Yeah. So I'll provide my own perspective. Maybe Chris would actually be in a better position to answer it, since he has personally done it. But I think he had alluded, and it will be the same three things that I'll mention, right? So let's say a product, market, and team. That's the thing. And I think that I wouldn't call it a failure, but it's very difficult to step away from the scientist mentality, which is to develop a solution and think the problem exists out there, which is kind of I wouldn't call it what most people do, and by no means a generalization, but it's definitely one of the traps that some people fall into. And there's also defining where the boundaries of research and development lie, and then focusing on value creation, because value is perceived differently in academia and in, let's say, in the commercial world. And that is a mind shift that needs to happen. And I've seen these two worlds clashing one too many times. Yeah. Chris, if you want to jump in on it, please do.
The three biggest risks in a startup are tech, people, and market, and so you want to de-risk them all. Getting to that academic mindset that also tries to make it perfect, or you're the best in the world, it's good enough, and now it can go out into the marketplace where you can get the feedback on this one feature we like, and the rest of the 9, why'd you bother with that sort of thing, is really, really key. And for especially the cybersecurity, you don't always have to. We're trying to find more and more areas where, and we found a few, it can be an enabling technology, because right now people, it's their insurance. If you put this in, your information is safe. We've also gone after, okay, what are the applications, what are the use cases we aren't doing right now because people don't trust them? Because then you can start to have an enabling conversation that put this in place. Now I can do X, Y, and Z, which I've wanted to do for the last 20 years. But no, you said it best. It's getting out of the academic mindset, getting into a commercial one, test early and often, be ready to pivot. That's an interesting journey to go from an academic to doing that, for sure. And one of the hardest too, just it's good enough. Let's get it out the door.
Maybe Mark, you can also comment on that, and then I will have a last questions, I guess, for this panel before we conclude. Please go, if you have something to add.
Not really, actually. I mean, we had to experience this change of mindset, but that's it, right? We are all learners, and we just did that.
And okay, and since we have,
it's good to know in advance.
Yeah, this is a good advice, right? So since this is my actually favorite question, since we have a very wide audience of students and young generation of students, doctorants, postdoctoral researchers, etc., who are currently looking for internships or maybe future work, is maybe you have some job places to promote in here. Please go ahead.
I think,
no.
Chris, are you talking to me or?
Oh, to both of you, to Mark and to Chris, maybe you have some open positions to promote. Yeah.
Go ahead, Mark. You want to go first, and then I can go.
What types of specialists are you looking for into your teams? What kind of specialists?
Well, a couple of things. It's not just quantum. Everybody hears quantum technology and they want to go and study quantum, but that's like 15% of the jobs. You need RF engineers, you need programmers, you need marketers, you need business people. So there's no one route in, which is maybe the first thing to realize. You don't just have to go through a quantum engineering degree to end up in a quantum company making a difference. Take advantage of all the, I mean, you don't even have to go through a PhD. You've got IBM with their open source stuff. I mean, everybody, Google, I'm forgetting Intel, there's more than a few, Microsoft, they all have stuff you can download on your computer and start playing. And actually that might be some of the insights. Someone with less experience with the real world that's not bound by sort of the classical notions, to trying stuff and spotting something crazy to do. So go have a play with that, what's out there. And if you are applying to companies, you're going to have to set yourself apart. So they're going to be looking for more than just an engineer, probably an engineer with that's thought about the commercial problem. So like if you apply to us, you're not just selling yourself as, okay, I'm an RF engineer, I'm an integrated photonics student, but also, even if it's naive, showing us that you've had to think of, and I think your first customer is X, and I've got an idea on how you'll make something that's a little bit more tailored to them. You're going to have to set yourself apart. Do a little legwork will go a long ways towards applying to companies, but hopefully there's some nugget of help in there.
Yeah, what I would add to that is that since now the biggest challenge for us was not to hire quantum people. When we needed people with quantum specialties, we always managed to find them. The challenge is to find non-quantum people, because in this case we're competing with like the whole world. But the fact that we work in kind of very futuristic business works well too. People are attracted to that, and I think you can see, right, the eyes are sparkling and they want to go and work in quantum.
Great. And Lucian, for Boston Consulting Group, what do you say?
It's a difficult one, simply because what I would encourage, and let me spin this positively, what I would encourage most people that are actually active in this field, and maybe this is the complementary of what both Mark and Chris have said, to develop some orthogonal skills would actually help you a lot more. So not purely being an expert in a narrow field, which most of us have done by doing it, but also acquiring a complementary skill that will allow you to communicate better and understand better the person that's sitting across the table and maybe doing completely something else functionally, will actually get you a long way ahead. So it doesn't have to be, let's say, a master, but even a couple of months or an internship, or I don't know, even talking to your business friends that you don't like because they don't do science like you do, or they don't spend time in the lab, will actually help you understand the other mindset, and in the end also develop your own a lot more. I hope that answers your question.
No, that perfectly answers my question. Thank you so much. I hope you could encourage also the young generation of scientists, consultants among our audience. And thank you very much for very interesting and inspiring presentations. And we were really happy to welcome you today. Thank you so much.
Thank you.
Thanks very much.
Thank you.
So we'll transition now to the third panel. So we've understood so far that, okay, we can have a quantum network and we have to secure it, but still there remains a few challenges, and we also need to discuss the future perspectives of the field. And for this, we have invited today two really exceptional speakers that have both an experience in academia and in the industry. So the first speaker will be Elam Kashefi, who is Director of Research in Paris at CNRS. She's also a professor in Edinburgh, and she's one of the co-founder of VeryCloud, as it was said just before. So she has co-founded the fields of quantum cloud computing and quantum computing verification, and she has pioneered a transdisciplinary interaction of hybrid quantum and classical solutions, from theoretical investigation all the way to actual experiments that happened and industrial commercialization. She has been awarded a few grants and awards in the UK, in the EU, and in the US, and she has served so far as an associate director of the NKIT Hub before being elected to the software activities within the Quantum Computing and Simulation Hub. The second speaker we'll have after Elam Kashefi is Noelle Godard, who's the CEO of QNect. She's also a portfolio manager at the Accelerate NY seed fund and an investment advisor at the CIF. She has joined the QNet management team in 2020, and prior to this role, she was a seed investor within the Accelerate NY seed fund, where she built a portfolio of 24 companies across deep technology and life science sectors. She has founded and led a few biotech startup companies, and she's an investment advisor also at the Cavendish Impact Foundation, supporting startups addressing unmet medical needs. And she's on board of MCorps, a nonprofit accelerator supporting clean tech manufacturing companies. And before all of this industrial activity, she was an assistant professor of physics at Hunter College, and she completed a postdoctoral fellowship at Harvard University, and she did her PhD in both physics and biology at Rockefeller University. So we'll start with Ellen. Thank you very much for being here today. We're really happy to have you to listen about your story.
Thank you very much. I know we have tested all of this thing. I'm hoping it's going to happen and I can bring it again, entire screen. Hello, let's see. You can see my entire screen. I'm hoping you're seeing my slide because I don't see you anymore. Is that correct?
Yes.
Excellent, good. So thank you very much for the nice introduction, for the opportunity to talk. I go quickly through the idea that I already mentioned by Mark, by others as well, and hopefully there will be more questions. Do you see my next slide now? Yes.
Yes, we can see you, Ilham.
Fantastic, very good. Just to make sure that I'm not talking randomly. So we heard that, quantum links are being developed, this QKD type of link, and we are seeing that the quantum nodes, quantum computer is being developed. Also, Frank has started talking about how we can link this together in the context of superconducting. What I'm showing is the experiment done in Delft, which are trying to connect the NV node together. So that's the beginning of birth of quantum internet, quantum network, quantum LAN, short metropolitan or long distance, whatever you want to say. So just quickly again saying that what we have been leading, as Mark also mentioned, within the context of the EU Quantum Internet Alliance, within the CNRS, we have been leading and together with Very Cloud development of quantum protocols, Zoo, which is a wiki of classified protocol. On top of that, as well as like a software library, which allows us to run this code, and industry use cases showing that part of it. And why I'm trying to repeat the story that Mark told you, because I'm sick of the people saying that quantum application beyond QKD does not exist. It exists. If you want to talk about them, come and talk to me and many other people. And I just wanted to pass this message. There is a wealth of protocol and application that exists the same way that quantum algorithm exists, quantum machine learning exists, quantum chemistry exists, and quantum protocol also exists. There is a huge challenge, which is the whole point of this session, to discuss how do we take all of this wonderful pen and paper protocol in the domain of quantum cybersecurity to the quantum actual domain of marketing, and we can discuss on that, but please do not mention there is no application beyond QKD. So now, what is the vision that I want to convey a little bit of it, of why we have a very exciting opportunity right now by quantum internet, is that because we are reconstructing this from scratch, if you wish. And there's a lot of lesson we can learn from the classical internet, the things that go wrong, that we can now trying to ensure that they don't go wrong again. And the message that is more and more is repeated within the community is that we can have the privacy, security, integrity by construction. This by itself is another talk, and I don't want to spend too much time, but I want to give you a glimpse of it, that what is so unique about quantum communication that allow us to have this if you like, by construction security rather than some sort of ad hoc afterthought added element of it. So we already mentioned the quantum cloud client server application, but I want to also mention one other thing about it, that again, people are these days super excited about quantum supremacy, quantum advantage, but in quantum communication, we already have those things. There was very recent work of my colleague Eleni Diamanti and others that show some quantum communication advantage. But again, this sort of client server application that we talk about, the quantum cloud, is something that is proven in a mathematical, rigorous way that cannot be achieved using classical communication. So if you're about the advantage, quantum communication advantage has been demonstrated and proven long time ago. We're just not that much into the hype. We actually want to implement these things. So again, it's very important to say that there are applications that we know we cannot achieve it using classical communication, and they are again beyond QKD, but we know that we can achieve it with quantum. So since we already heard enough about the client server setting, so let me show you that what is the next big thing. The next big thing that we are really thinking is going hand in hand with my claim that why we can build quantum internet from construction being secure is the idea of this distributed computing, or if you like, in the most classic type of cybersecurity scenario that you can think, that you have bunch of party, they could be malicious. Somebody has some algorithm, I don't know, let's say Microsoft developed the most recent fast quantum machine learning algorithm. Bunch of other people have the data. Let's say Amazon have tons of data, which want to run some of this clever algorithm on top of it. And Google built the quantum computer. And you want to make sure everybody is able to work together, but nobody trusts each other. And that's exactly classic scenario of the multi-party secure quantum computation. And this is something that we know how to do it. The protocol exists, and it's not about the enhancement, it's just the fact of how to be achieving these things. So the distributed, you can think of it many applications: privacy preserving quantum machine learning, distributed quantum differential privacy, and all of these things are natural extension of the client server scenario that Mark was showing. That is one of the targets for Very Cloud as well. So how does this extension goes? Again, it's just like giving you a picture that there is the very fact that we have quantum communication, this single qubit that by themselves has this masking, making sure that any of our communication already is randomized by construction, and then you put all the bits and pieces of teleportation on top of each other, and you're creating this quantum mask state that you can now run your computation on top of it. And all of these figures is not something you need to really look at the technology part of it, but this picture is something that is my message, and I'm going to stop after this saying that, the purple things that are in these pictures are qubits. And these are like, if you like, it's almost like a QKD type of qubit, if you want, for the simplicity. The beauty of this thing that we can bring the classical SMPC, the classical protocol that exists for this multi-party computation that has been developed for the last 30 years, and using those classical hybrid structure, we can make sure that this quantum distributed computation remain also secure. So the security of QKD is now lifted to the level of the computation that we want to do on top of this stuff. And then this building block that we have recently developed, and is of course, demand much more technology improvement, if you wish, compared to the existing network structure. However, it's something that is, since I was supposed to talk about the challenge and vision, and I want you to ask a question that what is this complicated figure, I'm going to finish in here. But we have recently put a project together with our UK colleague to really develop this notion of multi-tenant quantum data center that I would like to claim that is bringing the last two panels together. The very first panel was talking about how we can take this distributed quantum local network and connect them together. Second panel was talking about how to secure things together. And now we're really putting all of these things together to eventually run in a distributed data center, the fully private, verifiable, secure, distributed quantum computation, and many, many use cases that come in this framework. So maybe I stop in here, and I would be happy to answer any question that you might have, essentially pitching that the future communication will be a hybrid network of classical and quantum link, and the target of boosting efficiency, security, integrity is something that we can hope to achieve very soon.
Thank you very much, Ilham. And maybe before we go to introduction to Noel and to a cross-question section that we prepared for you, just a very quick one. So you have like this very transitional experience from academy to foundation of startup. You also participated in many different governmental initiatives and projects as well. So on your opinion, what is the key factor in order to accelerate the transfer of competencies between these, let's say, different sectors in the quantum computing and in particular quantum networks ecosystem? What is missing now, and what should be done and can be done in order to accelerate the development in the domain?
I would say that the coordination is very important. If the national program in France was not announced, I would have said that is missing, but luckily our president has already announced it, so it's not missing anymore. So I think coordinated program, I have been also involved a lot in the UK system. This coordinated program in UK started, many years ago, and this continuous education, everybody mentioned it, Chris and others, and Mark all already mentioned it. So continuous education, so expectation is well adjusted, so people don't think that like something is going to be delivered, quantum internet is going to be up and running tomorrow, so shall I start security? So this education goes hand to hand, and yet support for the startup, obviously, to make sure that, Chris beautifully mentioned that this is gap in between. So I think, seeing it, how the system works, seeing that how well the UK manage it, and all the wonderful news that we're hearing regarding France, I think we are in the beginning of a very exciting things that everybody comes together, like these seminars, this conference, that the webinar that you're running it, to make sure we are not missing. Academic are not ahead of industry or behind of the industry. People are continuously aware of the challenges and working together. So I think we are in the right time. And I'm hoping this coordinated effort goes together so people have the right expectation and picking up the right challenge, and yet have the support to take the risk and de-risking everything.
Great. And just that was very explicit, very explicit answer, but just in the continuity, I remember we already had this discussion with you. Do you think there is a sum of dependency on the cultural aspects between like the evaluation of this quantum initiative, quantum networks, like everything quantum in one country and in our one? So there is some cultural aspects in order how do people launch their initiatives, how do we launch the startups, etc. in this?
I'm a really bad person. I don't even understand British culture, neither the French culture yet, you know, so to answer you. But I think maybe I would put it like it's not the issue of the culture. I think the beauty of the quantum is that people are very well connected, despite the fact that the community is large, but everybody is aware of each other. There is competition between the various parts of it, but the lesson that everybody seems to, in a domino effect, what's happening in US, what's happening in EU, what's happening in UK, what's happening in China, what's happening in Singapore. So everybody is like a domino effect affecting each other's. And it's the common message that is over and over, saying that there is still a long, a long marathon that we are on top of it. So the continuous support need to come from the government, need to come from the national program, need to accelerate part of it. So I would not say that there is a huge culture, a different culture, you know, like some places it started with the national program and then the industry come to the picture. In France, there has been a lot of industry already involved in quantum and now coming together in the quantum. So maybe the pieces comes in a different order, but still everybody come to the conclusion that overall you need every player, all the players come to here to make sure this ecosystem is really up and running, and then we can start the competition.
Great, thank you very much. And I think it will be a good transition to Noel, who is joining us from New York, from United States. I hope it's not that much early at your place, Noel. So please share with us your amazing experience and also tell us about your startup Connect and your activities, nowadays activities. The floor is yours, please.
Thank you. I'm really happy to be here. Is my sound okay?
Noel, we don't hear you. Yeah, perfect now. Yeah.
Is this better? Is this better?
Yes, yes, you can start. Yeah.
It's such a pleasure to be here. Thank you so much for the introduction. I had prepared a few slides, but the slides will be actually on Connect rather than just on my background, which I think you're interested in both. Yeah. So, do you see the slides okay?
Yes, we can see everything. You can start.
So just to tie the themes together, again, what Alain was saying, and I think it's very true. I mean, we're in the last session, and to some extent what we're talking about is sort of the combination of the first two sessions. I'm the CEO for Connect, and we're a hardware company, but specifically what we're building is quantum repeaters, which is a very interesting and needed part of the future of these quantum internet sort of structures and architectures. And the entire idea is that we support distributed entanglement protocols. So as you heard in some of the earlier talks, we've talked a little bit about QKD and it being a point-to-point system. We've also talked about some of the progress which has been made using trusted nodes. So of course, China had a very notable achievement this year of having a 4,600 kilometer trusted node network shown, which also had 2 satellite links. While both of these are definitely very important milestones in terms of creating new technologies, there's always some concern that either they're limited distance-wise or that they're vulnerable at things like the trusted nodes themselves. So there's really a need for the sort of the next generation of hardware in order to support the larger vision of quantum networking, which is to actually distribute entanglement. And in order to do that, you need something which is colloquially called, right, a quantum repeater. And the promise of this, of course, is that it will be fully secure. So there are a lot of challenges in trying to build what we all hope to do, right, the quantum internet. And you've heard today many people talk about both the devices and the protocols. Basically, not surprisingly, quantum analogs of everything we take for granted in telecom need to be designed in order to host quantum information. Similarly, the protocols, which typically are transiting single photons, need to be created in order to be able to deal with that as well as real-world losses. And then something we concentrate on a lot at Connect is this idea of trying to patch in, very much like Alain was just saying, you know, the existing classical network is there, and we should be able to build on top of it in order to roll out the earlier versions of the technologies. So what we do now needs to be compatible with existing infrastructure. And we also have to think, there was a question earlier today about cost. we definitely have to think about what scalability means in order to implement these technologies. They need to be robust, they need to come out of a laboratory, they need to be able to operate without having constant maintenance, and they need to be affordable in order to put them every 25 kilometers in a network. So at Connect, our vision is really to build this product suite, which the whole suite together operates effectively as a quantum repeater. Our differentiation as a company is that everything we do is at room temperature, which for the quantum field, many of you probably know, is somewhat unusual. And we have a real concentration on the engineering part of what we do to try to build these things for field and remote deployment and compatibility with existing infrastructure, specifically telecom fiber beds right now. Our progress is such that we actually are going to be the first company to commercialize a quantum memory with our sales next quarter. And we've demonstrated some of our other devices on this test bed, which exists in it's just east of New York City in an area called Long Island. And the suite at the bottom of the page is really our product suite. Anything that you see here as a blue circle is a device which we're building. The large blue squares are basically racks which hold those devices. And this is something that I've shown as like a 3-node network. The way that this network works, basically hosts what we would call an entanglement swapping protocol. You have an entanglement source which exists in both of the outer nodes. That source creates a pair of photons. One is stored in the quantum memory while the other is sent to a swapping node. At the swapping node, the other side, the other node, sends also one photon. If we perform a Bell state measurement at the swapping node, then now the 2 photons which remained at the quantum memories on either node are now entangled. So you've distributed entanglement from 2 separate nodes now across the 2 nodes, the distance between the 2 nodes. And at Connect, we're building both the quantum devices, which are the source and the memory, as well as the support devices which make this possible. So something which is often overlooked when you're building real networks is that your devices need to actually work together, which is not so trivial in the quantum world. So we have things like frequency locks, which allow our quantum devices to work together, timing standards, because the timing which is required for these events is actually more stringent than what's done in normal networking now. And also active calibration devices, because if you're going to send single photons through real telecom fibers, for things like polarization qubits, which is what we deal with, there's drift imposed on those photons. So we have devices which actually measure the active drift and correct for it before the swapping event happens. We call these our support devices because they enable the quantum transactions to actually happen. So we have a great team. And with that, I will say I joined the team in 2020, January 2020. I was formerly with a state economic development effort for New York State called Accelerate New York. And I met the founders, Eden Figueroa, Mehdi Namazi, and Maël Clement, when they applied to our fund. And because of my physics background, they invited me to join their team as their company was growing. And I was very excited to do it because I think they had a great technology. And since then, we've expanded with a number of senior scientists and junior scientists that we've brought on board. So with that, I will come back and invite any questions.
Thank you very much, Noel. And that was real pleasure to know a bit more about what does the Connect work, and especially you are the one representative from the United States side, so we can resemble a lot of international speakers during this webinar, and to have a global overview on the ecosystem. Thank you very much. So since you've been talking a lot about the Connect, I wanted to go deeper into your background, into your experience, and my question would be like, why this switch from, because you have founded 2 biotech startups, 2 biotech companies, so why this switch into the quantum communication? Could you please tell us?
So I think in the initial introduction, so I started actually in optics and photonics. My early graduate work was all in what is more traditional physics. And I joined a program that was available in New York City at the time, that if you had done all of your physics background, you could then take the opportunity to do your biology background and continue what is then a combined physics and biology program. So because my later graduate school background was all in physics and biology, I decided to stay in that field. My postdoc was also in the same. So when I became a professor, I built a biophysics department at one of the local colleges in New York, the City University, called Hunter College. I'm sorry if you're hearing the sirens. I'm in New York City, so you're getting a little morning noise. Okay, hopefully that's better. In any case, when I decided to leave academia, it was only natural that the first companies I would found would be in the biotech space, because that was what I knew. But they actually were diagnostic. The first one was a diagnostics company using optics again. So I've always sort of done one flavor off of my original optics background, and a lot of the research that I was doing in biophysics was also developing optical techniques, etc., to look at things.
Yeah, thank you very much. And maybe the same question that I had like previously for Ilham on your side, on your perspective, maybe from the United States point of view, from the West point of view. So what will be the key ingredients for, let's say, supporting the startup and for growing the ecosystem, maybe better support from the governmental side or involvement of the industrial companies into this, or what is your opinion on that?
So as you are probably aware, the US is actually the slowest to come to the gate with the quantum support, which is interesting. I think China was first, Europe, very short thereafter, and the US was actually just this year announced in 2020, announced a quantum internet initiative. So I think our government was slow to recognize the importance of it. I also think that quantum computing in the United States, because of Honeywell and Google, and IBM and Microsoft has been something that's sort of looked at as being supported by very large companies. So it's not so clear what the federal role was. I do think that this past year was important because the Department of Energy and the Department of Defense in the United States decided to put real money into building centers, collaborative centers. And I think a theme that we've heard over and over again today is that you don't build the internet in a bubble. You do it with all of these strong partnerships between industry and academia. And in order to do that, you need some sort of umbrella support which encourages those interactions to happen and supports them. Because it's not always so natural for industry, which is very driven by the pain points which they need to answer. So for instance, telecom. Telecom in the United States, and also true in Europe, is very interested in better streaming technologies. Those always are at higher speeds, those are at higher bandwidths, etc. That's lovely, but that's not where quantum is going to be when quantum is released. So the quantum advantage, which is coming from quantum communications, is right now all on the security side. And it's not so clear that the US telecom companies need that in 5 minutes. And they need to be incentivized to work with the academic groups, etc., in order to both provide the knowledge base they have and the resources they have for test beds, etc., for the academics to actually be building real world tools. And I think academia needs to feed those also into startup companies. So something we've seen, at least in the past year, is that a number of quantum specific funds like Quantum Nation out of France, Quantum One in the US. So some of these earlier stage quantum funds are starting to crop up that are specific to quantum technologies. And that's a great sign for the industry because they'll take a risk on something which is a long-term product goal.
Yeah, thank you very much. And maybe the quick one, because before we bring Ilham also to a studio and we can have a cross question section between. So once again, you have with Connect, you have a wide range of products to propose to customers, starting from photon sources, and also you were the first company to commercialize the quantum memories that are able to operate into room temperatures and with a quite high fidelity. So once again, generally speaking, building an integration in new technology will require like an infrastructure, a special protocols, a special infrastructure which is already built. So once again, going back to a question of chicken and egg, in the perspective of the, for example, of the West, of the United States, do you think this infrastructure is ready? How fast it will take to build it, or the technology? The technology, let's say, speed will be still quite dependent on this infrastructure building.
So I think you're right to point it out. There are initiatives. So one of the reasons Connect is located in New York right now is that there is a collaboration between a Department of Energy laboratory and a university that actively has secured telecom fibers underneath highways. So it's real telecom commercial fiber. to be used as a quantum testbed. And the state of New York actually has 3 centers. So in upstate New York, northern New York, there's a big photonics cluster around Rochester University, Cornell University, et cetera. And then there's also a Department of Defense laboratory in northeastern New York called Air Force Research Labs. Each one of these places is building their own quantum testbed. And the goal, of course, is that all of these will eventually be linked together. So I think that's one nice sign of an initiative. There's another one in Chicago, which actually had quite a bit of press maybe 6 months ago, which is funded by several different center grants in basic science as well as the Department of Energy. The history in the United States of how the digital internet was started, which we all know as ARPANET, started really as a Department of Energy initiative. So again, this was a basic research agency at the government level who decided that they were going to support the connection of their laboratories through a digital internet. And there were private companies like BBN and Bell Labs who were involved in creating hardware and developing the protocols, which ended up being the foundation for what ARPANET became. I think that the same type of rollout will happen, at least on the US side, where this may be the first tier of customers is largely defense and government, but it's just a reminder that that's somewhat needed, because at least in the United States, there'll be communication protocols, et cetera, which have to be regulated. Those governing bodies will do that anyway. So, the hardware rolls out, the protocols get developed, things get tested. But the Department of Energy in the US in particular has a whole network that they can devote to connecting all of their laboratories. It's a very natural place to roll out the technology at scale. And then if industry finds that what's happening is impressive, then I suspect that the next step is that industry tries to adopt and partner.
Okay, great. Thank you so much. That was very explicit and very much interesting. We bring back Elham to his studio. Welcome.
Thank you.
And we maybe have a time for a last quick question, and I know Alex have one.
Yeah, I have a quick question from the point of view of context. We recently organized with Elvira a quantum hackathon in Paris, and what we realized is that despite all our efforts, it was extremely difficult to attract women in the field of quantum computing, quantum technologies. So if you had any advice to give to young women scientists today to enter the field, what would it be?
How to motivate the young generation of students to enter the quantum computing field?
Well, I don't know why they always ask me this question. Maybe I'm a woman. Is that they do that to you, Noel, as well? The point is, first of all, I want to clarify that quantum is a very feminine field. If you wish you know that in France, at least, the among the many pioneers of the field, the head of the hubs that are doing it, I can name forever many female colleagues. Sometimes almost my colleagues jokingly they said there is instead of the glass roof, there is a glass ceiling, that we cannot let the young women come to the picture. But I think generally saying that quantum, because it's a very young field and it's a very multidisciplinary field, there was no barriers. At least I feel it like this thing. And I mean, I want to still have 50-50 people in my team, and maybe they are 10 to 50. So it's not 50% of my team is female. But I would say that it's like the education part of it is that it's a young field. You don't have a very old people who are dominating, so there is no culture, etc. There's so many exciting things, and there is since female are very multidisciplinary, I hate saying these sort of sentences, but I say it anyway, depending from where you come, you can really get involved, whether you like coding, whether you like mathematics, whether you like physics, whether you like engineering, whether you like computer science, whether you like abstraction, whatever you like, quantum has a place for you. So I think in a sense, if you compare, at least I come from a traditional computer science, now maybe time to say it about physics. I have been in the field that I was really the only one, whereas in quantum, it is not the case that I'm the only one. So maybe that's a good message, that is a very open, and there is many initiatives already going there. So I don't think we need to do something particular. Maybe males should not get a bit worried that there is too many female coming to quantum. So you should better think about how to encourage men to stay in quantum.
Great. Or maybe we can bring more often great and inspiring role models as you and Noel, for example, and Virginia, who we had previously. Noelle, you have something to add as well?
I think Elam is totally right on about the age of the field is important. I think that one of the reasons that we keep noting that women are not so much in physics at the academic level has to do with the fact that, the academic timescale, when someone becomes a professor, they stay a professor for their entire career. And that doesn't allow a lot of opportunities and turnover. So in physics at the academic level, very often we might see it as a male-dominated field simply because the lifetime of those positions is quite long. But right now, because academic positions are not so easy to get, many students who are getting PhDs in physics are actually going into startup companies. And because there are so many quantum startup companies which are out there right now, I think it's way easier for someone who has that talent set to now join a team. And all startup companies are young and dynamic, right? They have to be, otherwise they don't survive. And it's a natural place. I don't know of any startup companies that have a culture which is really male dominated. In our world, it's all, what can you do, right? So if you're good, you should go and you should join one of these. But I do think it has a lot to do with the sort of age of our discipline right now.
Does it answer your question, Alex?
Perfectly.
Perfectly, yes. Thank you so much. That was really interesting, inspiring, great session. Thank you for your time, and hopefully we could see you on the next events. Thank you so much.
Thank you.
Thank you.
So I think we can transition to the last panel, which will be about the business side of the quantum ecosystem. And for this, we will welcome the two famous speakers that we have every time, Jean-François Bobier and Christophe Jurzac. Jean-François is a partner and a director of technology at the Boston Consulting Group. Since he has joined the BCG in 2004, he has partnered with clients across multiple industries on projects related to digital, software engineering, and deep technologies. And most recently, he has led the BCG efforts on quantum computing and technology and digital organization. And he's particularly well placed to discuss the place of quantum in the industry. And after Jean-François, we'll have Christophe Jurzac, who is a managing partner at Quantum Nation, who is the only VC fund in the world dedicated to quantum technologies. And on top of this is the president of Le Lab Quantique and also the treasurer of Quantix. So before having his business experience, Christophe was actually doing also quantum physics as he obtained his PhD with Alain Aspect in laser cooling of atoms. And since he navigated in the world of quantum technologies and also the energy industry, and he will tell us after this about his experience. So please, Jean-François, the floor is yours.
Okay. So do you have any questions? I didn't thought I was like having a conversation. So sorry.
So maybe I could have a question for you that could actually lead the discussion. So we had the feeling a few years ago that the quantum industry was kind of polarized. Either some technologies were mostly appearing in Asia, some others in the US, some other in Europe. So for you today, how polarized is the ecosystem?
It's a very broad question. So first of all, it's very clear for us that we have a very limited knowledge of what is happening in China. We know that they invest a lot in quantum technologies in general. So especially in quantum communications, but not only quantum communications. We know that they are doing quantum computers, for example, in Alibaba and Tencent. But it's very secretive. So some people actually say that there might be China surprise, that they might come out with some good technologies later. But it's very stealth, and we don't see them very much. Now, if you look at Europe and let's say US, definitely. We see a vibrant ecosystem for the moment, and I think it's backed also by the analysis that Michel Korek from Quantix has done. We see a lot of presence from the US companies, especially in hardware. We know in Europe we have some good nuggets, like, for example, Pascal, that Christophe can talk about. But unfortunately for us, it's still a field that is very much dominated by the American companies. And if we look at, let's say, corporate users, because that's also an important part, I think the picture is not so bad, actually. When you look at the actual people who are experimenting in quantum technologies, in Europe, we have a lot of good success stories. For example, Total, Airbus. So Elvira is working with BMW, but other German OEMs such as Daimler or Volkswagen are also investing. Even Bosch, for example, which is an automotive supplier, is also investing. In France, also we have like EDF. I mean, we have quite a few early adopters, I would say, in Europe, and in the US. I've been involved in many discussions, and let's say that the dominant sector in the US that is working on quantum right now, I mean, there are two dominant sectors. The first one is financial services, with massive, and I say massive, investments from the big banks such as JP Morgan Chase and Goldman Sachs. They work with every quantum software provider and every quantum hardware provider that is out there. You name them, they work with them. So they have a very massive research program, and they publish, they do proof of concepts. They are very active. And another industry which is active in the US is pharmaceutical industry. They even formed a group called QPharm. We have some European pharmas part of QPharm, but the group is more active in the US than in Europe, to be honest.
And especially in the field of quantum communication and quantum networks, what's your role inside the BCG to make this a bit more advertised in the industry to your clients?
So first of all, we're gonna publish in 1 week a publication on quantum internet and post quantum crypto. So I can share with you some of the findings, like live. So we did a research last year, and I mean, we started last year, and it lasted for a few months. We interviewed startups such as, for example, CryptoNext, that Christos know very well, but also people who do satellite communication and ID Quantic and other people who are operating in this space. And also on the user space, because for us it was very important, we talked to CISOs, so Chief Information Security Officers, right, of major institutions. We talked to telecom companies, we talked to cloud providers, to understand also what they would expect. And to be clear, we think that quantum communication and quantum internet is very interesting. There will be a strong niche in government, military, defense sector, because this is a sector where it's very important to secure communication. So you might be willing to pay extra to go to all the assaults, to secure your network. When we talk to private sector companies, and I was very surprised about that, but when you talk to Chief Information Security Officers, and we ask them very precise questions about that, to be honest, their answer was more like, if there is any threat regarding crypto and the security of our channels, we might be more inclined to do post-quantum crypto, so to switch protocols, stay in a classical hardware, right, but use more secure protocols. So as you know, there will be 2 protocols that will be published by NIST next year, or the year after next year. I always forget. So one that will be long public key, but less compute time, and one that will be shorter key but more compute time. Just to deal with some For example, when you're in IoT, you want to reduce compute time, for example, right? And when you look at the list of threats that these chief information officers are facing, the communication part, to be honest, is really at the bottom. The most important part is somebody clicking on the wrong link, you know, or bribery or zero-day bug or stuff like that. So those are top of the list, right? And they feel that if they first need to secure that before going into, let's say, for example, the communication between their London and New York branches. For example, if you talk to banks, they don't feel that it's a major problem. So they are willing to upgrade the security protocols. They will be doing that, and they will not wait for there will be probably a deadline. We don't know when. Maybe 2030, you know, to switch the protocols from RSA to the new protocols. They will start upgrading before to make sure they are on time, right? But they will probably stay with classical, so basically post-quantum crypto. So I don't know if it's the right answer, the answer you are looking for, but based on our research, it was really and it was surprising to us because we asked them very precisely. Let's say if you pay extra, you know, we ask you to pay extra for a very secure communication cable between, let's say, London and New York, for example. How much would you willing to pay? And the answer was zero. They would say no. It's really at the bottom of our problem right now. Our problem is 70% of the time is an employee doing something wrong, like clicking on the wrong email or whatever, opening up access to hackers, and it's our top problem, you know. So we need to solve that before we go and secure the bottom part.
Okay, but even though there are this type of discussions with the chief information or security officers, you also need to stay at the top of the state of the art when talking to your clients, right? So what is your interaction, for instance, to funding agency, hedge funds, VC funds, like the one of Christophe, for this type of work?
So we have been talking to multiple funds, and let's say in general, if I take quantum technology in general, quantum computing, quantum sensing, quantum communication, there's a clear interest and in let's say in funds to diversify in quantum technology in general. So of course, Christophe is very focused in there, but there are funds that were not focused in there that are looking to broaden their investments there, right? So they look at different opportunities, and to be honest, for them it's very difficult market to navigate because, as you know, it requires a strong scientific background, and making bets it's very difficult. Christophe knows that, even with his PhDs and so on, even for him it's difficult. So imagine, you know, funds that have no particular background. So there's a lot of interest, I can tell you. There are a lot of events that are pushing people to look at this more closely. So you probably heard 2 weeks ago that SPAC acquired IonQ for $300 million. So which is a lot, I mean, for a company that has a computer with a few dozen qubits. We still a lot of noise, right? So it's a lot of money, right? So it's a big bet. So we see a lot of interest and a need to diversify there. And I think we're going to see investments very soon from these funds. Given the level of discussion I'm seeing, it's definitely going to be more crowded. So Christophe, you'll have more competition, more investors.
So actually, that's a perfect transition, because Christophe, in his work in Quantum Nation, you can't invest in every single company that exists in the world. But do you also work with other funds? Do you advise them on a technical point of view or about investment on this ecosystem?
Yeah, of course. So, and I wanted to come back to your introduction. I think we are not the only fund. We are the first fund dedicated to quantum technologies. And I think for me, that makes a big difference. I think we were really early on. We started to make investments at the end of 2018. So we have 12 participations in the portfolio in Europe and North America. In computing, sensing, communication, and some of the companies you hosted here today are our portfolio companies. So I'll name CET and QNect in particular, who made presentations. But some other companies like CryptoNext, which is doing post-quantum crypto, have a close link also, obviously, with quantum internet and quantum communication, and the quantum computing companies as well, which have by nature, we have the opportunity to be connected through the quantum internet. Thinking about Pascal, neutral atoms, NOR Quantic, which is superconducting qubits, Candela, and Orca for photonics, which are naturally to be connected or networked through the quantum internet. So we have been pretty active in this field. Obviously, I think I'd like to make a couple of comments. The first is things are changing fast. So we started the end of 18. We're really the first, and it was not obvious to talk about these technologies. I, for myself, started in 2015, actually, trying to sell software for quantum computers when there were just a few qubits by IBM. It was online and D-Wave at the time. Now there are more platforms, obviously, more qubits as well. But the thing that has changed is that people now have figured out what to do with these computers and these technologies. And I think that's a sense also of Tribune that Jean-François and me published in Le Monde a couple of months ago. Really, we see a more and more industry taking this technology seriously, and not only wanting to do a proof of concept, POC, as people say in the community, but really looking into integrating these technologies in their workflows for serious, for business, for real money, for an impact. Of course, we're not at the point where these technologies are already integrated. We are not reached the quantum advantage yet. There is quantum supremacy, as you know, but the real commercial, practical quantum advantage has not been demonstrated yet for any application for quantum computing, and that's important. When this will happen, I expect there will be a big change, also industry, big acceleration, and this will impact all sectors, whether communication or computing, hardware and software. So it's important to keep in mind that we're still in a phase at the beginning of this industry, and things will happen over the next month, over the next years, and it's really hard today to even imagine what the quantum industry will look like in 5 years. I think there's potential for disruption. That's obvious. Will the machines be good enough? Will the networks, quantum communication, be good enough? That's still to be determined. But of course, we believe as investors that there's a possibility that this impacts tremendously the economy, and that's to keep in mind. And to answer your question about other investors, so we were the first, and what we've done is invest in companies at really early stages. For example, we were the first investor in Pascal, one of the first investors with QNect and CET. And what I see now, 2 years later, when we go to the next rounds of funding, the Series A rounds, for example, we have more interest from non-specialized investors, deep tech investors generally, who want to co-invest or even lead the rounds, associating us to the process. And that's really good news. We see, as Jean-François said, a lot of interest. People who really want to invest into quantum technologies. There are difficulties. First, the knowledge, the expertise, it's really not really widespread. It's really hard to have access to experts who have also commercial mindset, let's say, who see the potential of these technologies, not what they're good for today, which is limited, but what they will be good for in 5 years or 10 years from now. And that's something that's difficult. And the second point is I completely agree with Jean-François here. When you're an investor, you have to make a choice. You make just, let's say, 1 or 2 investments in quantum. if you have to make a choice and bet on the technology, it's super hard. I mean, our situation is different. We have a portfolio with different time horizons, different hardware technologies. As I said, we invest in atoms, we invest in superconducting qubits, in photonics. So we have really a portfolio approach, and I think that's super important, and that's part of the value proposition as well. Doesn't mean we don't know where to invest, therefore we spread and we invest everywhere. That's not the case. We make choices. We invest in the best companies that we find. But if I was if I was an investor just making one investment in quantum, that would be tricky. That's really hard to decide what to do because there's no obvious metric, for example, to compare quantum computers, quantum computing hardware, and that's the same also for quantum communication. Do I go into QKD? Do I want quantum networks? What's best? Or where should I invest? Or post-quantum crypto? Still a bit unclear. So that's difficult, and I think things will clarify, but for now, I can recognize that there's a genuine difficulty in making the choices and picking the companies to invest in.
Thank you very much, Christophe, and thank you very much, Jean-François Bobier. That was very interesting, and I think that many of us and among our audience, we could have a better understanding the specific of your profession and all the challenges and difficulties that you have to overcome actually in order to move forward the ecosystem as well on your side. We are a bit out of time, but I think it's just because we had so many amazing speakers, like awesome role models that could inspire. I would say I always want to support like a future generation of the quantum computing scientists, and not only scientists, the startup founders, the investors, the consultants as well. So just in order to move forward this technology and to progress all together. So I think it was a perfect conclusion with Christophe and Jean-François to our webinar. What do you think, Alex? Maybe.
Definitely agree with you.
Yeah, maybe we can close here. Thank you very much to all for your participation. There are still some questions where we couldn't answer or our speakers couldn't answer. So don't hesitate to post them still in continuity in the comment box in YouTube. We will invite our speakers to go there and to respond to you directly. And thank you very much one more time for joining us. It was a real pleasure to host speakers, to host you for this event. Thank you.
Thank you.
Have a good afternoon. Bye-bye.